Only three of you only?
Good evening, sir.
Good evening, Rishabh. Only three joined so far.
Sir, wait, sir, I will inform, sir.
Okay, okay. Joe? Hello, Joe.
Yes, sir.
Good evening, good evening. So, was everything going well for you? How do you find? How do you find the course? Are you able to follow what's going on?
Yes, sir. It's going well.
Fine, right?
Yes, sir.
So now 6 joined. So let me start anyway. So last class I have given for steady flow some these what happens when you consider the steady flow. Of course, when incompressible steady flow, in fact. Okay, so that's an incompressible steady flow. So that is what you have seen, that rho is constant. In that case, you have seen this is what is the always constant. This one, ls t square, ls t dot product divided by 2 plus this p by rho plus that g into z, that potential, the external force potential, that's basically constant. So you usually consider when you consider, for example, certain flows, p by rho plus gz itself consider it as some kind of pressure. Okay, so z is basically z direction. For example, when you consider sources, what will happen? You don't generally consider that z. Okay, so because there's no meaning, no. So z, if you consider two different places, for example, source. That means what? Usually for a fluid, where the depth is there, right? So in the depth you consider as your Z. Here it's going from infinity to infinity, that source point to all directions infinity. So generally P by rho plus Z Z that we consider as hydrostatic pressure maybe. So you don't need to consider. So forget that is actually constant when there is nothing. But when you are in the case of that source flow, we generally consider pressure without that GZ thing. Okay, the external force thing without we will not consider. So you will see that one. So um, having done this hydro, so another advantage of this hydrostatic thing is P by rho plus GZ equal to 0, right? So that will give you some kind of you will see some applications like Archimedes principle, those kind of one or two examples I'll come back and do. Before that, let me check if you have three-dimensional source, for example. Okay, so if you consider that three-dimensional source, so what is the three-dimensional source that you have you done three-dimensional source? We have not done, right? So we have done only two-dimensional, right? So two-dimensional flow only we have considered using stream function, that source or sink. Right now we'll look at this three-dimensional source. Okay, so let me use this source in 3 dimensions. How does this look? Source in 3 dimensions. So how does this flow field look? Because it's in the 3 dimensions, right? Usually you have a point in space and it goes all directions. Only direction source means it only go in the radial direction, isn't it? So you expect the source for this flow, the flow field, okay, the flow points only radially. What is the meaning of this? That is u, the vector u, if you put it in the r theta phi, for example, spherical coordinate system, if you consider, because it's the 3 dimensions, right? So you'll have only some function of r like you did earlier, only in the direction of r cap. Okay. So the only thing is source you're considering at origin. Okay. Isn't it? So f of r means what? So because otherwise if your source is at some other point, you have to write f of x is your source, some fixed point minus r. Okay, so at x equal to for example r equal to mod x. Okay, so r x minus x minus some point. So that's what you have to consider. So this is basically r is what mod x, right? Mod x is a vector. So we consider x, y, z is like this. If there is a fixed a, b, c is the source, okay, you call this some a, then usually we consider r as mod x minus a. This is how you say. Okay, so if a is the source point, okay, here this is the case. If 0 is the source point, origin, then r is basically this. Okay, so just for writing, let this one, then r is this if a is the source point. Okay, so this is how you get your flow velocity is only in the direction of r. So the only component will be r cap component. So in spherical coordinate system, now you need to get that spherical coordinate system. So what is your del dot u? This is your del dot u should be 0, right? So what is your del dot u? What is the del dot u? That you need to make it 0, right?
Yes, sir.
Since del dot u equal to 0, so del dot u in spherical coordinates. Okay, so what is that one? So that I'm writing directly del dot u now we are in 3 dimensions. Okay, so you'll have, I'm writing directly, just go and verify. Okay, just list one component only. So dou square dou r of r square into fr. Okay, so this is the one you will get as del dot u, that is equal to 0. Can you just recall why is this so?
Yes, sir, because yes, we know the divergence of the formula, sir. Any
Uh,
vector, then
okay,
that equal to F1 by HV, HU, HW,
inside you
like that,
have,
sir.
so you have this one. This is your now you need to solve this equation. This PDE, if you try to solve, what is that you get your solution? Can you give that solution if you to find this del dot u equal to 0? What is FR you will get? So F R square, any R is anyway positive. So you will
Sir,
have uh,
open del R.
so basically, yeah, that's all. No, so R square into FR. This is the only derivative, no? So R square F of R equal to constant, isn't it? So this implies F of
Yes,
R
sir.
directly as some constant. Let me call this. Uh, let us call this some C. Okay. So you'll have a C by R square. C by R square is your F of R. Okay. Now, now, now what happens? Your flow vector now. Flow vector is now you will get what do you get here? So what is that you have? C by R square into R cap, right? That's what you have. This is the flow. Implies this is the one. So what is that constant? If you want now to get the constant, last time what we have done in 2-dimensional flows using the stream function, we derived for source and sink. You put some strength, right? Let M be its strength. Okay. Let M be like earlier. So M is the strength of the source. So if you consider this, what is that strength of the source? How do you find? So in 3 dimensions, you will have this point and around you have. So consider some circle. Okay. So whatever the flux that goes out of any circle of radius R. Okay. So let us say some radius of R. R can be even 1 or anything. Okay. So if you consider that, for example, you take this one. So whatever so the flux that's your strength, right? What is the strength? That is the strength, right? So strength, how do you get
Yes,
that one
sir.
last? How do you know that? What did we define the strength last class or early lectures? Did we define the strength?
Yes, sir. You have defined, sir. Actually, I forget that formula, sir.
Let me check. So we'll once we clear only we'll see. So lecture 16 we didn't do, no? 15 we have done. I'm trying to open your WhatsApp one. So just and we did that source thing, stream function, source. Okay, and then yeah, source and sink we have done. And how did we define this one? Finally, you get C by R. C is stream function. So the stream function, what happens there? We have a stream function we derive directly. So because we know the stream function for source, we actually, how did we get that C? Source strength, the volume, yeah, that we have defined already. No, same thing. Source strength means basically the strength of the source means the definition itself is like your volume flux, right? Volume flux of the fluid from the source point. That's your definition. Okay. So that means M equal, I already defined. So this M is nothing but, so how do you define now? Now you have, this is your surface, 3-dimensional surface, 3-dimensional sphere. Okay. So this is in 3 dimensions. Now point is 0 and you have the CR or whatever the disk. Okay. So in this basically is SR sphere. Now let me call this SR. So SR is that sphere. Okay. So this is what is your sphere. So this sphere, whatever the source, because of the source at 0, whatever goes out, that volume flux means by definition, this is our I'm putting semicolon so that that's already defined. This is over this SR, that sphere, this whatever the flow, the velocity going normally, n cap ds. ds is surface area here, okay, because we are over SR. So this is what, this is equal to, what do you get here? So a by r square, right? So your c by r square. Basically, you have c by r square as your r. So r n cap is what? What is your n cap?
Sir, it is volume vector perpendicular to surface.
Surface. That is your r cap only, no?
Yes, sir.
R direction. Okay. Since n is this, so what you are getting is c by r square, r cap dot r cap ds over sr. Okay. So let me go to the next step. So this is equal to r goes. Okay. So c by r square over SR, right? So this is your this thing. Yeah. Now R square goes. No, it didn't go, right? So what is that we did? Yeah, well, that's okay. C by R square. Where? Over the surface, right? So only on the surface of the sphere. Surface of the, this is the surface of the sphere. Okay. So, and SR is the surface of the sphere. Not inside, okay? Sphere means only surface, no? Hello? So basically
Yes,
SR is the
yes,
surface.
sir.
Okay? Surface, basically you have to understand, okay? So this will give me, what do you get? So I didn't cancel it anyway. So here, let me, don't cancel it. So I have, this is your R square. Now what do you do now here? This is actually C by R square. What do you get here now? C by R square will be as it is, right?
Sir.
R is anyway fixed, no? So on this SR, this R square is nothing but this is over this is it, R equal to R, right? So you are on SR. So this is over basically SR, and this is C divided by capital R. R is fixed, right, for your sphere. So this is anyway 1. And this into ds. What is the that you give? R is fixed, so C is constant. Comes out integral SR ds. This is the surface area. What is the surface area of the sphere? C by R square into 4 pi R square, right? 4
Yes,
pi
sir.
R square is your surface area in 3 dimensions. So now this R square goes. So you'll get C into 4 pi as your source strength. Okay. So now we go to, so that will give me actually, once you know what is the, in terms of M, I can get my C. So this implies C equal to M by 4 pi. So this implies you now you have U is actually, now you have FR, right? So C by R square into C is M by 4 pi. R square is usual small r square into R cap. So this is your flow variable now. Okay. This is what is your basically your flow. This is the source flow of strength M in 3D. Okay. So this is how it looks, the flow. That's what you want, no? Source flow, basically that's what you want. Now this what else it needs to satisfy? So we have shown that del dot U equal to 0, right? We are considering why del dot U equal to 0?
Because incompressible fluid, sir.
Incompressible fluid you consider. So where did you consider your where did you consider that density? Density is constant, right? How you get the density constant then? Yeah, we are only dealing with incompressible fluids only. Okay, so that's okay. So that's only for incompressible fluids. This is the source. This is the source flow. Now, for steady flow, what will happen for steady flow? For steady flow, what is the equation now? Steady flow, Euler equation becomes dou u by dou t becomes 0, no?
Yes, sir. Because it did not depend on time, yes, sir.
Yeah, can you give that Euler equation? What happens to your Euler equation now? Yeah, can you get me the Euler equation? So for steady flow, Euler equation is this. That is momentum equation basically. Okay, I'll write Euler or momentum equation. Euler equation or momentum equation. Momentum equation is what? Use rho into
Rho into
du by dt equal to minus grad p plus external force, right? B. This is your external force, right? We put d only, no? B. So if you rewrite this is actually we are actually dealing with incompressible fluid, right? So you will have rho into dou u by dou t plus what do you get here?
sir, here, sir, we get rho gradient of rho into u vector.
U dot del u, right?
Gra- Yes, sir, yes, sir, yes.
Actually, you will get both of them, right? U dot into, yeah, this acting on you. That's okay. Yeah. So this is equal to minus grad p plus b bar. Okay. Now assume that this there is no external for steady, as you see, but because we are dealing with the source. Okay, that's what I was telling, since we are dealing with, we are doing since we are looking at source flow, b equal to 0. B, when you consider B is basically gravitational, if you want, assume that B is 0. Okay, this is an assumption. This is the assumption. Okay, assumption. So otherwise you have to consider gravitation. So, but you don't know exactly, no? That height only you have to consider. That is complicated. So we are simplifying, looking at the simplest cases. So you see this one, dou u by dou t. Anyway, steady state, right? So for steady state, this is equal to 0. So you will get rho into u dot del u. U dot del u or u dot del u, right? So this is what you have to write. This is how you have to write, right? Isn't it? So this is equal to minus del p. Now, since we are considering only steady flow. So what do you get here now? Now I'm trying to use it here. So rho into, yeah. Now you will have to use again those formulas. U. What do you have? U. U is
So,
your,
m
let
by
us say, UR component. What is your UR component? The only component that you are m by 4 pi r square, right? M by 4 pi r square. Okay. What else? Dodo r of,
yes, sir,
dodo r of f of r, right? M by 4 pi r square.
yes, sir.
Anyway, we have written already something similar, right? So where did we write that one? Say just some time back. Where did we write something? Yeah, this is there's del dot u. So here you are dealing with u dot gradient of. So this you will have to check. So if you check it, it is going to be like this. Okay. So by finally this is a vector, right? So you will have a r cap. So just go and verify this one. These things you need to verify. LHS is this. LHS. This is in spherical coordinate system. So LH is this, which is equal to minus grad P. So P is the pressure. Okay. So now this is your RHS anyway. So which is RHS. Okay. So this having written LHS, we write RHS. So what is that you get now? This if you differentiate 1 by R square only, you're differentiating now. So 1 by R cube it will become. So you'll have finally R power 5. So you'll have m is anyway constant, m square comes out. Divide, and rho is anyway constant, divided by R power 5, 4 pi. So is there anything else you will get? Minus 2 divided by, right?
Yes, sir. Minus sign also. Yes.
Minus 1 by, so you minus 2 divided by R cube. So 2 goes, so you'll have 2, 1, 1, 2 left. 2 into 4 is 8, 8 pi square. 8 pi square is with negative sign, of course. Negative sign equal to minus grad P. So this will give me actually what is my pressure difference, right? So what is grad P in radial coordinate? What is this one? Minus
I
dou
think.
P by dou P by dou R only, no?
Yes, sir.
Grad P. Only in R cap direction, this is the only thing. Okay? Now this is what we have written. So now immediately you can calculate your P. Dou P here. Okay, so this is your dou P. This is because in spherical coordinates. Grad P in spherical. Just write it so that you remember why you need it. So this will give me minus goes both sides. Now if you integrate, so P will be equal to, if you integrate, P will be some constant. Okay, from 2 points if you do, so fixed points, let us say some fixed point, you integrated some fixed point to some R. If you do that, so that's what R integration constant you put it, and this side, and you are integrating 1 by R power 5, right? So you'll get a negative sign, minus m square rho, that's constant, 8. So 1 by R power 5, right? You need 4. So another 4 you multiply and divide, so that you will have
32.
52. See, I already cancelled this both sides plus sign. Okay. Now you still get minus. That's why you're getting minus. 32 times pi square R power 4. This is what is actually your pressure. Pressure inside the, once you have a source, this will go like this, right? So any point here, if you consider, the pressure is basically, if you calculate, what is P naught? So P naught, you actually see, this is an integration constant right now. So what actually P naught? Where P naught is actually, this is the pressure, where pressure at
Origin.
R goes to infinity, at infinity. Okay, move away from the source. Okay, pressure away
Yes,
from,
sir. Yes, sir.
P is actually pressure away from the source. So you should write it like away from the source. Away from the source, that is as R goes to, that is at infinity. That is at infinity, right?
Sir, in spherical coordinates, sir, why we are using, sir, radial velocity vector? Why we cannot use all the components, sir?
Because it's the source, right? All only flow directions only in the R direction only.
Yes, sir.
Physically, that's how it looks. So you're interested only to derive the source flow only, nothing else. No other source,
Okay.
no other flow.
Okay, sir.
So as you see, at R equal to 0, you will have infinite. So basically, what happens at R equal to 0?
Pressure will be zero, sir, I approximate.
R equal to 0. So you'll have that is the source. You cannot calculate. So you give R equal to at some point. Uh, what happens at R equal to 0? You'll have that pressure will be high, right? R equal to 0. What is that you get? I think this is what is where P is this one. This much you can say. What else? What else you can say? Away from pressure. For example, here you want to calculate pressure. So initially there will be a lot of pressure here, right? this pressure, so away from, so as you increase R, okay, so you will have, you fix one R, let us say up to here one R, okay, so in that R you will have some pressure, so that P naught, whatever that P naught at infinity, that is what it is.
Sir, if we put R equal to 0, then it
Uh,
will be like minus negative term will become, sir. Like P equal to
yeah,
P naught minus something negative infinity.
no, you that's what, you don't look at that way, so you don't know exactly the pressure is. See, what we are concluding from this is only this one. Yeah, it appears to be like that, but only, but R equal to 0, there is nothing, no source. Source, you don't see anything, no, you cannot calculate.
Yes, sir. Yes, sir.
So moving away, maybe the direction doesn't matter, the negative thing. So P pressure is only, acting on the fluid element only, you take positive because it is going outward normal. That's how you are getting minus infinity. That's how you have to say, right? That's still okay. R
Okay,
goes
sir.
to
Okay.
0, R
Yes,
goes
sir.
to
Yes, sir.
0. Of
Clear.
course, it is becoming more and more thing. But
Yes.
as for bigger R, as if you increase R, what happens if you increase R? Uh, if uh, if R is increased, what happens? R is increasing. Pressure is
Pressure will
actually
be
reducing, no?
pressure will be
Reduction,
reduced.
right? With increasing R, the pressure is actually, what is that? How do you see the pressure is not in this direction. So you have to see in this direction. This is the pressure direction, right? The force acting on this, right? So here you have to see what is the pressure. So if you look at here inside, what is the pressure? So it is actually increasing, right? So as
Yes,
R
sir.
is increased, actually the pressure increases, the P is increases. That means, what is the meaning of this? See, as you increase R, so basically P naught minus something, no? You look at from infinity. From infinity, you look at from infinity. You at infinity, it is the pressure is P naught, right? Now you look inside the, from 0 to 0 anyway, it is going to be, pressure will be infinite, right? So from 0, if you move away, or you coming from infinity, if you come, you reduce, okay? So I'm just looking increase from 0, okay? So I'm writing here from 0. If you want, you can write so that, then P actually increases here. So if you think that it's coming from infinity, what happens infinity? At R equal to infinity, that is P naught, and you take somewhere inside. Inside, if you take, what happens? The pressure decreases, right? That's what you naturally see. See, at infinity is P naught. Now you little from infinity to something come down, less than infinity. Okay. Now, but it is finite. What happens? P naught minus whatever divided by that radius, whatever radius power R. So you are actually removing, no? It is actually reduced. But it is opposite if you go from 0 to infinity. Okay. Is it fine? So this is tricky way I'm writing, but this is same as if R is finite, then P is basically P at infinity minus that whatever m square rho by 32 pi square R power 4. We're writing whatever same thing. So basically here this decreases from infinity to R, right? So now we are looking from 0 to R. Okay, from the origin. From the origin to R, if you opposite direction, this basically increases. If you come from infinity to R, if you come, basically it decreases from this naturally. That's what you are saying. Okay. Any question here?
No, sir. Sir, it will come in exam, sir. Today's class also.
Now, see, this is only, you look at only three-dimensional source. Okay. So whatever we are doing today, we are considering for the exam. Okay,
Okay, sir.
so don't worry about it. But whatever I'm teaching, just learn. So hydrostatic, whatever hydrostatics that I want to do, that we did know last class, hydrostatics, right? Hydrostatics are fluid statics where you consider the U equal to 0, so that basically our equation is simply grad P equal to F, right? I'll just show you what it is. We wrote like this, right? So grad P, yeah, this is for steady flow. And yeah, basically this is the one. Without external force, if you consider, right? This is the external force, right? GZ means what? GZ is basically your external force. Grad P. Yeah, this is the one. This is the one is basically your hydrostatistics. So its application, I will come back and do some other time. Okay. So let me right now, I'll try to do something. So we have done three-dimensional source. So you so far what you have done using the source using the what is that one, stream function. Using the stream function, you actually derived the source, sink under one or two flows there. Okay. What is the application of basically what is the use of source function? Okay. So let me write simply use of stream function. Use of the stream function. I'm going from 2-dimension, 3-dimension, right? So this is that is simply that we here so far for the sake of giving source in 3 dimensions I have given. Okay, so you have to understand that way. So here for steady flow we have considered steady, right? Source, because it doesn't change, with time. It's constantly it's going function of r. Time variation is going in the same straight line, right? So that's why it's basically steady flow only you consider source flow. That's what you have done so far. Okay. Source flow in 3 dimensions. This is the first 3-dimensional flow that you have done. Now coming back to 2D. We are doing 2D. So 2D, so use of stream function. Using the stream function, you have given some source, sink, and what else you have done? Vortex flow you have shown, right? Last class in using the polar coordinates. Yes.
Yes, sir.
Now, what is the use of this one? So basically, the problem is in 2-dimensional flow. If you consider, so these are your streamlines. See, along the streamlines, you know that psi is actually constant, right? A equal to constant is your stream, right? That's your stream function is constant. This is maybe psi1. This is your psi equal to C2. You consider 2 points in your fluid. Okay, let's consider R0. Okay, so this is your vector. Okay, R0 and R1 be 2 points. 2 points in the plane only, right? We are only in the 2D in plane, and we know that in the 2-dimension you have a stream function exists. Psi is the stream function. Then you consider any 2 points. So basically, I consider this point and this point, right? So now you connect this with some curve C. Okay, then the volume flux crossing any curve C. Okay, so volume flux crossing any curve C. So this is the curve I'm talking. Or if you want to put it as gamma. Okay, so we put some curve gamma. Gamma is the curve. This is the curve connecting. This is your R1. This is your R0. Any curve gamma. What is the flux that you give is you actually get your psi at R0. Basically R0, R1, R1, R0 minus psi at R1. That is the volume flux. Okay. you are going from R1 to R0. Okay. So let us say this is the direction if you integrate, for example. The gamma is in that way. So what is the volume flux? So how do you prove this one? That's the advantage, right? So you pick up 2 points. Suppose you have a stream function exists in your for your 2-dimensional flow. Once you have the stream function exists, psi is the stream function that exists. You take any 2 points and you connect it by some curve gamma. Then the volume flux, that is what that volume flux of the flow passing through this gamma. Okay, crossing this one. So that is exactly is equal to this difference. The difference means the simply constants. That is actually equal to R0. That is C1 minus C2. Isn't it? So proof will be simply a volume flux. We know the volume flux. Volume flux is integral. Where do you go from where to where? So you're going from R1, this point to this knot, let us say. Okay. So we put the direction. So you will have this one. You're going from this point to this point, and volume flux means you know. So U dot n cap ds. Okay. This is a line. So you simply line. This is a line. Basically, ds is basically line element. Small ds is arc length. Okay. So if you want to say ds is the arc length. Arc length of gamma. Now, how do you evaluate this one? This is equal to, now you know the stream function, right? So you'll have R1 cap, R1 bar, R0 bar. What is u in terms of stream function? Dou psi by dou y, right? U component is dou psi by dou y. V component is minus dou psi by dou x. That's how you derive not 2-dimensional dot product with. Now you have this curve gamma. Gamma is, what is the tangent? Tangent to gamma is, once you parameterize, what is the tangent? You don't parameterize, that's okay. So it's simply x and y, right? This is only 2-dimensional curve. 2-dimensional curve you can represent like x of s, y of s. Okay. So gamma s is basically, gamma is x of s, y of s. S is the arc length. S belongs to I. Okay. That's how you are doing that, R1 to R0. So this tangent to this is simply dx by ds, dy by ds. Then what is the normal? Normal to gamma. So dx dy is a tangent. So you will have dy minus dx. This is your normal. Dy by ds, dx by ds. This is actually your normal. So why? How do you check this one? Suppose I want my tangent to be parallel to x-axis. Dx equal to 1, dy equal to 0, isn't it? So now you come back and put it. What happens here? D normal to gamma. Dy is 0 and minus dx is minus 1. So it is basically going towards. So if you are going from, if your curve is this one, curve is this way. For example, curve is your x-axis. You are going from 0 to infinity side. You are moving in this direction. So right hand side is normal, right? So this is your outward normal. So here the tangent is 1, 0. So here this will be 0, minus 1. So this is the negative y direction, right? So this is your y direction, positive y. This is your negative y. You understand? So that's how you fix this one. So this I think I hope you already know. So I'm just writing here. So you just put your n cap ds. Now just this is formality. We'll have R0 to R1 to R1 to R0. Anyway, this is a point, no? So I'm just fixing point at some point, no? So once you so okay. Now once I put ds, you cannot put this as r, right? Now once you put this one ds, once you write n cap as dy by ds, this thing, so you'll have to change these numbers, right? These are simply the points, that fixed points. Anyway, psi at these points only, no? R1, these are simply points in the xy plane. So you still you can write bars. Okay. So what is this one here? Dou psi by dou y into n cap. You have dot product. First component is dy by ds. Dy by ds. That ds and this ds will go. Okay. So plus dou psi by dou x into dx by ds into ds. So this is nothing but r1 to r naught cap equal to into this is what is this one? This whole thing dx by ds. D psi by ds, right? Total derivative only divide by ds. So d psi by ds. Total derivative by ds. This gets cancelled. So nothing but if you integrate simply integral psi d psi. So psi at r naught minus psi at r1. So endpoint. So if you are going from this point to this point, r1 to r naught. Okay. So this point to this point. So basically that is your r naught at r naught first one. That is your C1 to C1 minus C2. So a volume flux you can actually calculate. So what is the advantage? This is the two-dimensional flow. No? The advantage is if one simple observation is you take like this. I have two streamlines like this. So here these are the 2 points. What happens here? So the distance is the volume flux across this is something. The difference between C1 minus C2, isn't it? What happens if I consider here? Here you consider what is the volume flux here. Here also you have C1, C2 only, no? Isn't it? Hello?
Yes, sir.
So that tells you that basically a gradient, that rate of change, spatial dimension rate of change. So what do you call this? Gradient of psi is actually constant, right? Either these 2 points or these 2 points. So what happens here? So what do you conclude here? So basically this is your volume flux. Volume flux is basically constant across this, right? That's what you have to say. Okay. So what you have to write is okay, from this, if you consider this, I will write like this. You have a volume flux between these points. Let's call this AB. This is PQ. Okay. This is AB. This point is A. This point is B. This point is P. This point is Q. Let us look at this. So if here volume flux is this volume flux from A to B is same as this volume flux from P to Q. So that's what we can conclude, right? So but your flow is same. It's only two-dimensional. N cap ds. Now what happens here? So if this is actually both are same, right? Both are C1 minus C2. So that is same as some constant, same constant, right? So what happens here? So when this is reduced, volume flux needs to be finite, no? You have a volume flux. Volume flux across, what is the meaning of flux? Basically, a flow across these 2 points. That should be constant between these 2 points. See, you reduce, no? Suppose you have a full lot of area through which if you are looking at it, some bigger circle, for example, imagine just bigger circle through which you already have a flow. Through which what is the amount of fluid that crosses that full big area? You'll have more, right?
Yes, sir.
That fluid content will be more, and you try to reduce that circle into diminish it, very small circle. Obviously you will see that that you will see less fluid will go out, isn't it? But now here
Yes.
it says the same constant.
I
The
think the
velocity.
velocity will be increases, sir, when we
So that
reduce the.
means yes. So that implies what is the conclusion is the u increases across p and q. Okay, increases if p minus q decreases, right? Basically A
Yes,
minus
sir.
B, A minus B decreases, you write, so that you understand. So A minus B, that difference, A minus B decreases. So that's why you see the nozzles, no? When you have the constant flow, steady flow, if you have, once it, from bigger area to smaller area, so the flow velocity has to increase. That's what it tells you. So in two-dimensional flow, that is what you are seeing here, little mathematical. Okay. So this is called, this is basically the advantage of this application. You can think of as application of stream function. Okay, you can define your flows. You can define different two-dimensional flows. You can define through stream function. Another advantage is basically you can see this application where you can calculate the difference between these streamlines. That is basically, that's how you calculate the flux across some curve. So if I ask you, I give you some, in some two-dimensional flow, if I ask you, what happens if I give you some two-dimensional flow? Obviously, you know that there is a stream function that is there. You can calculate the stream function. Once you calculate the stream function across 2 points, what is the flux if I ask? Obviously, you can easily calculate this through this formula, right? That is the advantage. So you don't have to calculate. So now we simply write what is the streamline there, what is the streamline at this point, and passing through that point and passing through the other point. You take the difference. That is the constant. That's all. That's what you have to do. Okay. So across two streamlines, if you don't have to calculate anything, so you simply take the difference between those constants. Streamlines are constant. Stream function is constant, right? Across the two streamlines, volume flux is actually constant. That's what it tells you for the two-dimensional flow.
Okay, sir. Sir, I have some doubts regarding the equations, conservation of mass momentums and energy conservation, sir.
Okay, tell me what is that you have?
Like, sir, you have derived for the all Cartesian coordinates, sir, all the equations in Cartesian coordinates. So I am
Yeah.
trying to derive in the polar coordinates and cylindrical coordinates. I am
Mm.
asking, sir, ki I need to derive from the starting to polar coordinate, या at the end whatever result I got, like differential form या integral form, that result I can convert in other coordinates.
No, no.
Like,
You see, for you, equations means don't look at the integral thing. Only differential equations only you write.
okay, sir. Okay, sir.
See,
Like,
you don't have to look at that integral forms.
okay, sir.
Because you don't know how to see what is W we consider now fluid element. That is only in Cartesian coordinates. Cartesian
Yes, sir.
coordinates you have to put it into in terms of r theta phi. That is difficult, no? That you don't know exact. See, finally
Ye-
it is all same only. Same
yes, sir.
WT, but only thing is r theta phi coordinates you have to take it.
Yes,
Then
sir.
inside is anyway same integral, same differential equation, but in r theta phi. That's
Yes,
okay.
sir.
That's same only, no? What is the doubt there?
So, like, sir, I'm thinking ki derive the start from
No,
Cartesian
no, no, no,
coordinate.
no, no. Don't derive anything. Only simple conversion only you have to do.
Okay,
See,
sir.
you
Okay,
you
okay.
simply take W there. W is function of capital X comma T. Here
Yes, yes, sir.
W is
Here,
simply r theta phi. That is a vector comma T. That's all.
okay, sir.
If it is a WT, if there is no W, it's fixed thing. It's simply W means r theta phi. W
Okay,
of
sir.
r. At every point you can represent in terms of like x, y, z. No, so here r
Yes,
theta.
sir.
That's the only thing.
Like, sir, we got our differential equation, differential
You
form
don't
of
have.
the
You
mass.
don't. You, no, no, no. You don't derive again.
Okay, sir. Okay,
I
sir.
don't want you to derive. There is nothing to derive. Only convert it.
Okay, okay, sir.
Once you have
Okay,
in
sir.
uh, once you have in that Cartesian coordinates, polar coordinates or whatever coordinate system, simply whatever the I have del dot u I can convert,
Yes, sir. Yes,
right?
sir. Yes, sir.
I,
Yes,
I
sir. Yes,
have
sir.
do t. You know how to write there. Do
Yes,
t
sir.
no change. No, you are not going to change anyway.
Yes, sir.
Do t no changes. No, you are only writing spatial coordinates only. No, so del
Yes,
dot
sir.
u you can do. del dot, grad p, for example, grad of scalar function, you can always do there again. Grad,
Yes,
that
sir.
grad thing in r theta phi. Okay.
And
Similarly, what else? That
divergence and
del
curls.
cross,
And
divergence and curl.
yes.
Now, that is the only thing you do. Don't derive anything. Now fix
Okay,
in
sir.
your
Okay,
mind
sir.
whatever the derivation I have done for the Cartesian coordinates. Just focus on that. Make sure that there is no doubt. You ask only on that, so that
Okay, sir.
if you understand. Okay, just a minute. I want to tell you something here. So this is your first course, no? Fluid dynamics.
Yes, sir. Yes, sir.
This is your first course. Don't expect that I did fluid dynamics. Now I'll work directly. So even if you are working in fluid dynamics tomorrow, MTech project or MS or whatever you do, okay, PhD, still you will be going through the some advanced means basically the fluid dynamics equation. Same thing only, but little advanced way you will understand later on. Okay. So this is the first
Okay,
course
sir.
where you are concentrating only on simple equation derivation. First, of course, simple whatever the fluid properties, flow properties, and these equations you derive. Okay. And then looking at the simplest flows that you are considering. So you have to get familiar first.
Okay, sir.
If you are familiar only when you are taking some advanced fluid dynamics or something next course, that will be useful.
O- Okay, sir.
So you keep see it is like you how you suppose you are using some calculus in your when tomorrow when you are working at some industry your or higher studies your academic some institute you are working and you are working on some problem and you want to understand you're doing calculus. What is that you recall? You only recall what you learned in your undergraduation, no? Which book you
Yes, sir.
followed, which book you followed, that book only you open and try to see those formulas, right?
Yes, sir.
Because once you open, then only you understand how they are derived. All it's easy for you. After all, we are humans, right? So you
Yes, sir.
understood this book, this notation, but finally everything is same. But no, having understood here and then tomorrow, and while using, if I look at some other book now, because I know everything, I understand. But the human mind that is not you are not familiar with those notations. Notations may be different that time because it's a
Yes.
different book. So similar way here, you try to understand the equations that I derived, if you like, okay, or if you don't like what I derived, some other book also fix it first. Okay. So I suggest you whatever I have given, if you whatever I have given, just try to understand everything. Fix it. Get familiar with these equations. Every time you only work with these equations. Any textbook you take, what is that book? What is that you are considering some momentum equation? Immediately, what you derive only you write. Okay. If it is, you just see whether they are same or not. Okay. It will be same only. Okay,
Yes,
so
sir.
whatever
Yes.
you are learning in your undergraduation, so that should be in your mind always. That's what I want to say. Okay.
Yes, sir. Yes, sir. Actually,
Uh,
sir, I am trying to drive from the scratch like in polar coordinate. That's why I'm confused. So that's why I'm
that
asking
is
to.
it's only conversion. You don't derive anything now.
Okay, sir. Okay, sir.
Okay. So
Understood, sir.
now let me just 10 minutes. I will try to derive some vorticity equation.
Okay,
Okay.
sir.
So but for the exam, I think I didn't tell you something like that flow is irrotational implies there exists some scalar function such that u is given as grad phi, right? Isn't it? So u is equal to grad phi for irrotational flow, right? Isn't it? In two dimensions, you 2D only you take. So same 2D, I will have this is equal to del cross 0, 0, some psi of xy, isn't it? This is your stream function. Yeah,
Yes, sir.
this is for incompressible. So if you consider irrotational and incompressible, if you consider, you have this is also true, this is also true, isn't it? So you have a stream function which is constant along streamlines, isn't it? So what happens if phi is constant? along, what do you call them? You don't have to
That
say,
is
but we call them equipotential lines. Equipotential. Potential is same along that curve. Okay, those curves. Equipotential lines. So this meaning is, this definition is the lines along which phi is constant. Isn't it? So you have a grad phi. Phi is anyway scalar function. So if phi is constant alongside, for example, when you derive the flow, you can easily see certain flows. You may find, or you can actually find what is your phi. Phi is a function of x equal to constant. If you put it, those are all your equipotential lines. Okay. So put some constant phi. Once you calculate phi, see what you did. Psi is a function of xy. Now you put equal to c. Then you may see some circles in the vertex, right? So vertex flow, what did you see? You saw those circles. Those are your streamlines. Okay. See, for example, these are your circles, right? Vertex flow. These are your streamlines, right? These are your streamlines. That same flow, you try to get your phi. So here u bar is your flow. So u bar equal to grad of some phi for the same flow. Okay. This is equal to this one. So you see, find this one. Now, once you find this phi equal to constant, if you put it, those are all equipotential lines. Equipotential lines. So for vertex flow, equipotential lines will be like this. What are these lines? Lines, how do you represent which is equal to constant? Yes. Those are simply linear combination. Ax plus by equal to c, right? Isn't it? Any AB. Isn't it? This is 0. Ax plus by is basically equal to c means what? These are lines passing through 0, 0, right? Hello? Maybe 0. Yeah, like this.
yes, sir.
Something like this. So you should have you will have to see exactly what it is. Okay, so you try to find out for the, at least I have not done it, so I'm not saying anything here, but obviously you will see like that. These are called, I just want to say that these are equipotential lines, where if you calculate this phi, okay, phi you calculate, without calculation also you can see, you can say something. Okay, so without calculations, how do you say what is your u? What is your u in terms of stream function? U is equal to dou psi by dou y, and here dou psi by dou x. So what happens here in the streamlines? Dou phi by dou x into dou phi by dou y, isn't it? Yeah.
Yes, sir.
So now you can see this is what is your flow in terms of stream function, in terms of potential function. So one can see, you may, simple calculus, you may ask you can create some question based on this. For example, what question you can see is something like this phi equal to constant and psi equal to constant. Can you show? Now I'll just give the exercise. Show that streamlines and potential lines, equipotential lines. Okay. Let me write it as equipotential lines. Or perpendicular. That is, what is that you want to show? Can you show this one? So what is the streamline? Streamline means psi equal to constant. Okay, and C1, let us say, and phi equal to constant C2 are perpendicular in the plane, in two-dimensional flow, right? Basically, they both exist only in the two dimensions, right? So that's what you are doing here. So you can
Yes,
easily
sir.
show this. You can easily see. Okay, with your simple mathematics, whatever you learned in your calculation
Yes,
can
sir.
be.
We can take the multiplication of both slope equal to -1, sir.
Yeah, you do show that one. That is simple exercise. Okay. So I think
Okay, sir.
I'll stop here and maybe or shall I proceed and write? Maybe I'll stop here. Next class I will do this vorticity equation, and there is something called Kelvin circulation theorem. All those things we'll see. Huh?
Okay, sir. Sir, from Monday, sir, our exam will be started, sir, and it
So
will.
this week you will not have classes, is it?
Sir, our exams are till 26
Uh,
September, sir.
okay, okay,
Because
no problem. So we will not have classes, right? That's what you are saying.
yes, sir. Because sir, some of the students have taken minor courses. That's why,
Okay,
sir.
okay, 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 fine. So now tomorrow, Monday, you are writing exam, my exam only. No, I already sent the question paper.
Yes, sir. Yes, sir.
You now have 16. This lecture also I will share right away. So anyway, same lecture 16 and 17 I combine. Same file I have written. So now I will have some 5 pages only. So go through everything and try to understand. And based on this only, I'll give you some simple questions. Okay.
Okay, sir. Sir,
Do
in exam, sir, derivation will also come, sir. Like whatever you have derived for curl, divergence, and
yeah.
different.
See if I don't give simple ones, if I don't give, for example,
Okay,
most of
sir.
them are simple. Simple one, if I don't give, you never work out and you never get familiar. At this age, you should get familiar only by working out,
Yes,
remembering
sir.
it.
Yes.
Working
Yes,
out
sir.
only will. So you'll have to twist your hands with pen. Okay. So
Yes, sir.
you try to go through this whatever I have given. Okay. So
Okay, sir.
simple question paper only you try to work out. So it is going to be some 30 marks question. Why 30 marks? I do you know it is an unusual procedure there.
Yes,
Midsem
sir.
30, midsem 30, endsem 30, and
No, no, sir. End sum is 50, mid sum is 30, and internal is 20 marks, sir.
okay, fine. So okay, all right. So endsem this portion plus that portion together we have to give.
After, sir, it's depend upon you, sir. If you want to give some portion from this before midsum, you can give. Otherwise, sir, after midsum for end
Mm.
sum examination, whatever you will teach for us
I
after midsum,
understand. I
that will be the
understand.
for end sum, sir.
Yes. Okay, no problem. We will see. Huh?
Okay, okay, sir,
Or
sure,
we'll
sir.
scale. It doesn't matter. Don't worry. See, don't worry about the exam and this. Now try to work out and learn.
Okay,
Okay.
sir, sure, sir.
Try to focus. Put your mind and solve whatever what you remember. Only few things. Whatever you learn, you remember, and you work out based on that.
Okay, sir.
So
Okay, sir.
don't get panic when you look at some problem. Oh, I don't know something. Something strange. Those things don't look at it that way. So these are the rudiments you should be in your mind. So get familiar, work out whatever you learn. Look at it again and again. Just scribble it here and there. You try to get familiar all these lectures. Then now we attack the problem. When you look at the problem, now you only look at the problem, keeping whatever you learned in your mind. Based on you recall one by one what is required there, you solve it. Okay.
Okay, okay, sir. Okay,
So
sir.
that way, what will happen? You understand how to attack a problem and solve it. And anything outside the person, anything if you cannot, then you will just look for the extra information. Okay.
Okay, sir.
So this is how you have to learn. Anyway, so that's
Okay.
my learning, my style. I told you, people have different styles. Okay. So I'll see you
Okay.
anyway. The paper is sent. So we'll meet again on 29th then.
Yes, sir. Yes, sir.
Huh? Okay, I will
Yes,
share
sir.
this file today, and yeah, we'll see you.
Okay, sir.
I'll
Thank you,
deal
sir.
with Professor Nikhil about how to evaluate your question papers. Huh? 11 only, no?
Okay.
Yeah,
Okay, sir.
just
Okay, sir. Okay. Thank you,
okay,
sir.
see you. Yeah.